You can do it after I'm done. Where are we going to go with this? We're going to review a bunch of terminology. We're going to remind ourselves of some common fertilizer materials. We're also going to look at some vocabulary that talks about common application methods. I'm going to show you how you can convert from the oxide form, because that's the form that phosphorus and potassium are expressed as in fertilizers, to the elemental form and back and forth. And by the way, that is fair game for the exam, so do bring your calculator and do know how to do that. We're going to talk a little bit about how to figure out how much fertilizer you need if you know the recommendation. And then I'm also going to talk about liming materials and their characteristics. We talked a little bit about why a lime yesterday, but the stuff about the products and the traits of the materials themselves actually belongs in this unit. So we'll talk about that today. So first of all, what is a fertilizer? And it's a compound that contains at least one plant nutrient, okay? So in the case of ammonium nitrate, the nutrient is nitrogen. It contains one nutrient, although it contains one in the ammonium part of the molecule and one in the nitrate. In the case of potassium nitrate, it actually contains two, both potassium and nitrate. It only has to contain one, however, to be a fertilizer. Now, no fertilizer materials are 100% of any nutrient because as products exist in the near Earth surface environment, those elements are always combined with something else, okay? I mean, there is pure nitrogen. We're breathing it in, but you can't use it to fertilize the plant, right? It's inert. And actually, pure elemental phosphorus actually ignites when it's exposed to the atmosphere. And pure elemental phosphorus, you know, K with nothing else in the compound, actually burns when it contacts water. I remember, you couldn't do this anymore in a chemistry class, but I remember when I was taking chemistry, the chemistry professor had this material in a vat of water. It turns out it was phosphorus, and he picked it up, you know, with pincers, and it frothed, and it was amazing. Now, that's against OSHA laws, I'm sure now. You couldn't do that, but this was at the time when you could still do that. He just wanted to make a point that you would never leave that particular element on the table exposed to the environment. Turns out it was phosphorus. So where do nitrogen, phosphorus, and potassium originate? Well, nitrogen originates from the atmosphere. There's the Haber-Bosch process. Josh referred to it a little bit yesterday. Monumental effect in terms of its impact on human populations. Developed by a German chemist and a German engineer. The engineer was from BASF. Basically bought out the rights to it from this little chemist who was working at a small university in Germany. As Josh said, the emphasis on getting a cheaper, more reliable source of nitrogen was to produce munitions. It had nothing to do with feeding. P and K, on the other hand, originate from earth materials. Phosphorus in fertilizers originates from rock phosphates. Some of them are igneous, some of them are sedimentary, but they're hard rocks. The potassium originates from potassium-bearing minerals, typically in old oceanic marine deposits. They usually exist as either chlorides or sulfates. So nitrogen comes from the atmosphere, and P and K comes from earth materials. Here's a nice map of the world phosphorus deposits, and you can see that we do have some deposits here in the United States. Florida is our big place. There's North Carolina, and there's also some in the Idaho-Montana area. And phosphorus is pretty widespread across the world, too. Realize that nutrients for plant and animal and human nutrition are considered kind of quasi-strategic in the sense that you need them to produce food and feed your population. Folks are certainly concerned when they're only in one part of the country and not well distributed. So phosphorus is rather well distributed. I couldn't find a similar map for potassium, but you can see in this pie chart that Canada has well over half of the world's known resources in potassium. Russia has a bunch. Belarus, which is a former USSR republic but now independent, has some. Germany, where potassium deposits were first discovered in the mid-1800s, still has pretty substantial deposits now. Our potassium resources were pretty extensive in the 1920s when they were first discovered, but they've been largely used up, and most American potash now comes from Saskatchewan, Canada. We did mine it out near Carlsbad, near the caverns, but not right next to the caverns, for a number of years. There's a very, very rich deposit there. But again, it's been largely exploited, and we don't have a whole lot left. It is important that our resources to grow food be well distributed. During World War I, there had not been a good deposit of potassium located on the North American continent. As a matter of fact, most of the exploration around the world hadn't happened yet. The known rich deposit was in Germany. It was tightly controlled by a cartel of companies, and when that arrangement fell apart, the government actually took it over. They controlled the prices. American farmers were very unhappy about the amount of money they had to pay for potassium, kind of like an oil cartel, but this was a potassium cartel. And then when things heated up in terms of rancor coming into the 19-teens and it looked like there was going to be a fight, the Germans cut off the supply entirely. Okay? So it is good that resources that we all need be well distributed so that if you have a difference of opinion with folks, you can still get something that's as strategic as a nutrient someplace else. Okay, how do we describe the nutrient content of fertilizers? And this is something that just drives people crazy. So let's understand this as we're talking about it today. You might find a bag of something at the Home and Garden Center or your fertilizer dealer that says it's 5, 10, 15. You need to know what each of those numbers refers to. The first number refers to nitrogen. Okay, the second number refers to phosphorus as phosphate, not as elemental phosphorus. And the third number is potassium expressed as potash. Okay? Nitrogen, phosphate, P2O5, and potash, K2O. That's what the numbers refer to. And that's often referred to as the fertilizer guarantee. In the case of nitrogen, it's a total nitrogen. In the case of phosphate, it's citrate-soluble phosphate. In the case of potash, it's water-soluble potash. Now, there are times when someone might expect you to be able to convert back and forth from phosphate to phosphorus, from potash to potassium, and vice versa. And these are the constants. You need to do that. They're based on the ratio of molecular weights. So if you were a hotshot at chemistry, all you need to know is the molecular weight of oxygen, phosphorus, and potassium, and you can figure these out yourselves. If you're interested in that, I'd be glad to show you. If not, you just want to remember at least one of these, because this number is the inverse of that, and this number is the inverse of that. So if you remember the number for phosphate to phosphorus and potash to potassium, you can get the other constant by dividing one by it. It's the inverse. But this is fair game for an exam. They might say if a material has 25% P2O5 on the fertilizer guarantee, what is its percent phosphorus? So do know how to do this, because I consider these to be a couple easy points. Common nitrogen fertilizer. Ammonia is a nitrogen fertilizer in highest concentration. However, it's a liquid under pressure that at atmospheric pressure goes to its gaseous state where it's stable, so it has to be injected. I don't know of much ammonia use in Maryland. In other states where I've lived, it's been the #1 material, but it certainly isn't here. Ammonium nitrate, of course, was used for a long time. I understand that it's hard to get that now because of Homeland Security regulations. Is that true or is that a myth? It's true. Okay. Urea appears to be the #1 product I'm hearing about right now. Ammonium sulfate, that's a good one because it not only has ammonium, but if you need nitrogen and sulfur in a situation, you can get both from that product. And then there's the UAN solutions that are mixtures of urea and ammonium nitrate, and they come in 3 concentrations, 28%, 30%, 32%. Urea, well, let me say that a lot of the nitrogen fixing plants, a lot of the nitrogen production plants in the United States have closed down. You need natural gas to both fuel the process and as a feedstock. And as natural gas prices have gone up and fertilizer production has gone global, it just happens that our companies can't compete on the worldwide market. So a lot of them have closed. A lot of the nitrogen comes in now from China. It comes in as urea. I think you know why when you look at the list. Why would you make urea and ship it around the world rather than ammonium sulfate? Yeah, that's right. More nutrient for the buck. That's what's made. So urea has some issues in terms of volatilization losses if you apply it to the surface, but I think we're going to have to get used to using it and using it effectively because it is taking over as the #1 product that's out there. All nitrogen fertilizers the same in terms of their efficiency, how much of the nutrient is taken up by the crop compared to what you put down. And of course the answer is no. If you put ammonium-bearing fertilizers or fertilizers that convert to ammonium on the surface and leave them on the surface, you can have volatilization losses. Okay? Dr. McGrath showed you yesterday that you can get volatilization from manure. You can also get volatilization from urea and from UAN if you apply it to the surface and leave it there. So no, the efficiencies are not the same. There are actually some recommendation adjustments even in Soil Fertility 1, and that's the Mimeo that has all of the fertilizer recommendations for agronomic crops. Actually, there's a recommendation made to increase your rate by 15 to 20% if UAN is surface broadcast at planting. Increase it by 5 to 10% if sidedress N is dribbled on the surface, and a 25% increase for sidedress surface applied urea. So those adjustments take into account these volatilization losses that occur. Now there's some products out there now that can reduce the amount of volatilization, and I'll talk about those towards the end. There's also some less common nitrogen materials. Typically you're going to see these in the horticultural and specialty trade. Sulfur-coated urea has been around a long time. Basically it's urea coated with sulfur, and the nitrogen can't get out until the sulfur is broken down by sulfur oxidizing bacteria. Urea form has been around for a long time. That's a mixture of urea and formaldehyde. Methyl urea, isobutyldiene diurea. Sometimes you'll see these in products that have slow release or partially slow release. Turf industry uses a lot of these. If you have a mixture of both urea and IDBU, you only have to go out and fertilize your client's lawn once instead of a couple of times. So if you have an end user who's willing to pay for that convenience, you can afford to buy them. They're not used in agronomic crops, to my knowledge. Common phosphorus fertilizer materials, of course, superphosphate is a standard for a long time. It's very hard to find that now. It's low analysis. Triple superphosphate, 0.46, monoammonium even is dropping out of favor, I understand, in favor of the diammonium phosphate. And then there's a bunch of ammonium polyphosphate. So there's a wide variety of things out there. The good thing about superphosphate, along with ammonium sulfate, is that in addition to the phosphorus, you also got a big recommendation for sulfur. Common potassium materials, muriate of potash, sulfate of potash, potassium magnesium sulfate, that's sold under a name Sulpomag. It's a trade name of, I don't remember the company offhand, and potassium nitrate. Most of the potassium fertilizer in the United States is sold as muriate of potash. It's the cheapest form out there. It's the first product of purification, and so it's cheaper to produce. Okay? But if you've got a chloride-sensitive crop, and some crops are sensitive to chloride, you might have to use one of these sulfate sources because for some things, the amount of chloride you would get with your potassium actually does damage and causes yield reductions. So unless you've got a chloride-sensitive crop, you usually use muriate of potash. In terms of types of materials that are out there, there's both solids and fluid or liquid. The solids can be one of several groups. First of all, they can be granular, and that's when the fertilizer materials were mixed together in a liquid state before the material was dried. So every granule has the mixture of nutrients. Okay? Another option, and I'm not sure how widespread it is here, is bulk blend, and that's produced by just mixing fertilizer materials, physically mixing them to get the fertilizer guarantee you want. Again, I'm not sure. I know there's bulk blending going on in Garrett County, but I don't know how widespread it is east of Garrett County. One of the problems with bulk blending, and this really caught on nicely when it started because it gave a plant fertilizer vendor the opportunity of just making whatever mix his clients wanted. It looked really easy. But there were a lot of problems encountered with it. If your materials aren't the same size, you have really serious problems with differential settling as the truck with the fertilizer bounces down the road. And people found that what they got delivered was not mixed anymore at all. A lot of those problems have been rectified by making sure that your materials are similar in particle size when you purchase them for your mixtures. There's also fluid dealers here in Maryland. Some of them sell solutions where stuff is totally dissolved in water, and in other cases there's suspensions where there's a clay material mixed in there to keep stuff in suspension. So a farmer has a lot of options in terms of the type of material he wants to add in terms of its physical conditions, as well as the fertilizer guarantee that might be there. I just want to talk about bulk blend for just a moment. Typically, these are relatively small units. They have stocks of materials, and they have some kind of a mixing apparatus. And again, they tend to serve a limited area because their reputation is that if the stuff is transported too far by truck, you get a differential settling, and you no longer have a mixture where it's delivered at the farm gate. 1919 is a good example of a bulk blended material. And if you were at one of these plants and you were making 1919 out of this mixture of stuff, you had DAP, you had urea, and you had muriate of potash, you could figure out how much of each of those you needed so that you had 19% nitrogen, 19% P2O5, and 19% K2O. Okay, the fact is when you add those up, you don't quite have a ton, though. And so in that case, you actually have to add a little bit of a material. It's often called a filler or a make-weight material that makes up the rest of the weight. If a guy's buying a ton of stuff with a certain guarantee, he wants a ton of stuff with a certain guarantee. And sometimes a filler is necessary when you're bulk blending. If you have high analysis materials like urea and DAP and muriate of potash, you usually don't have to add much filler. Again, when bulk blending first started, we're talking 25, 30 years ago, some of these high analysis things weren't available, and in some cases there was a pretty substantial amount of filler that needed to be added. What's added depends upon what's cheap in your region. Sometimes it's a coarse sand, sometimes it's a coarse limestone. Whatever doesn't cost a whole lot of money. So there's ads on the radio right now. I think it's Scott's, but it's geared towards the homeowner, and they say, oh, no fillers in our fertilizer. Okay, you're probably granulin. Okay. So the question often is, well, what's the rest of the stuff in that bag? You know, if this is 0060, what else am I paying for? And I think a common assumption is because it's not 100%, it must have filler. Well, that's not true. Remember I said that there isn't a fertilizer out there that's 100% of a nutrient. There's always something else in the compound with it. And so in this case, in muriate of potash, which is pretty simple, muriate of potash is nothing more than KCl. Anybody here use light salt or alternative salt products? Well, light salt is a mixture of sodium chloride and potassium chloride. This is potassium chloride in that. All right. Potassium chloride is 52% by weight potassium and 48% chlorine. So is there any filler in here? No, there's just the other stuff in the molecule where the nutrient is that's part of that compound. Okay? No filler in this. So I get a little cranked up about this notion of filler and people using the term incorrectly, in case you haven't gathered that already. So just so that we clearly understand what's filler and what isn't, we already talked about this. This is 0060. It's potassium chloride chemically. It's called muriate of potash in the fertilizer trade. Now, is there filler in this? No. There's potassium and there's chloride. Okay? Now, here's the case where there's filler. You make meatloaf. Why are you eating the meatloaf? Why do you eat meat for dinner? Protein, right? You want protein. Now, there's other stuff in it. There's fat. You might be eating it for the fat, but most of us aren't eating it for the fat. There's also water in the meat. Now, you put in some seasoning so it tastes good. And if you grew up in a family like mine, you put some extender in it. You know, you put in oatmeal, you put in crackers, or you put in breadcrumbs. What was the purpose of that? It That's right. Spread it out and serve more people, right? And they still got the sense that they were eating meatloaf, but there was other stuff in it. Is there filler in the meatloaf? Yeah, the filler is the cracker crumbs or the oatmeal or the bread crumbs or whatever it is you use, okay? There's actually filler there. There's no filler here, okay? Filler is something else you add to a material kind of outside its primary use. Okay, some application terminology. Broadcast. You're spreading the fertilizer hopefully uniformly across the whole field. Could be, usually I think this term is used in the pre-plant mode. Top dress. You're putting it on top of a growing crop. It's what we typically do in March on our winter wheat. Side dress. You put it alongside of the row. Typically what we do with corn, hopefully when it's 9 to 15 inches tall. Starter. This is fertilizer that's put typically next to and below the seed, about 2 inches over and 2 inches down, so that there's a small amount of fertilizer readily accessible to a young plant that might be experiencing some low nutrient levels, particularly early in the spring when movement of nutrients is slowed down a bit by cool temperatures. Remember we talked about diffusion yesterday. Diffusion is slower in cold soils than it is in warmer soils. Fertigation, okay? Here you're irrigating and you're adding nutrients with your irrigation water. Incorporation, okay? Somehow that material is getting under the surface. Perhaps you're applying it and then coming back behind it with a tillage implement. Injection, this is what you want to do with a smelly manure so that everybody within a couple miles of you doesn't complain to the local health department about odors, okay? This means you're putting something below the surface. Okay? So certainly fair game for an exam question and something you want to be able to understand yourself is how to get from a recommendation, because often a nutrient management plan has a recommendation for the amount of nitrogen, phosphate, or potash. The choice of the material is up to the farmer and what he can purchase. Now, if you're a fertilizer company and you're doing plans for your customers, you can go all the way and recommend the product. But if you're a public agency like us, you can't show preference for one vendor over another, and we give you the recommendation in terms of N, P2O5, and K2O. So then someone, either the farmer or perhaps the fertilizer representative who's helping him try to figure out what's the best product to buy, is going to make this decision. Nonetheless, it is fair game for the exam. So let's say the recommendation for a soybean crop was 90 pounds of potash per acre. You don't need nitrogen on soybeans, and this soil apparently already had enough phosphorus. It was above 100 on the FIV. And of course, the cheapest potassium product out there is muriate of potash, 0,060. So the question is, how much muriate of potash does he need to apply so that he gets the 90 pounds of potash per acre? And there's a series of questions you need to ask yourself. What's the recommendation? That should be in the plan. What's the preferred product? Call your dealer, see what he's got, compare prices, get the best deal for your money in terms of pounds of nutrient, not pounds of product, okay? What's the nutrient content of what you decide is your best deal? And then you need to calculate the amount of preferred fertilizer product to apply to meet your recommendations. Now again, if that's intuitive, and I hope it is to some of you, just do it by whatever method you want. If it's not intuitive, let me say that you need to recognize what your recommendation is. You need to look at how your product is labeled for the nutrient content. 0,060 means a 60% K2O. You need to express that percent as a decimal fraction, and you divide your recommended rate by the percent nutrient expressed as a decimal fraction, and 150 is the pounds of muriate of potash that you need in order to apply the 90 pounds that were recommended of K2O. Again, fair game for the exam that you're getting prepared for. Okay, so let's look at this one. 60 pounds of phosphate are equivalent to how many pounds of P? Okay, remember I told you you needed to go back and forth between P2O5 and P, K2O and K. How many pounds, if you have 60 pounds of P2O5, how many pounds of actual phosphorus do you have in that material? So go back and look at that slide and tell me what factor we need. What factor do we need? What do we need to multiply P2O5 by? 0.44, okay? So hopefully you know that. You know the one for P2O5 and you know the one for K2O. And which one of these numbers is a little bit less than half or 44% of 60? Yeah, you know it's not 12, right? It's too low. You know it's not the same, right? You can eliminate some right off. And hopefully you've got a calculator with you that day and you can figure out the rest. Okay, how about another one? A producer wants to apply 60 pounds of nitrogen per acre to his orchard grass pasture. If he uses ammonium sulfate 2100, how much material should he apply per acre? Okay, he wants 60 pounds of nitrogen and he's got a material that's 21%. Okay, now I took math in an era where they expected you to estimate stuff, and I know that, you know, there's 5 20s in 100. Okay, so what I would do would be to multiply 5 times 60 and know that it's pretty close to that, right? Now, maybe you're not an estimator and that doesn't work for you. But do you agree that C is the right answer? Okay, so know how to do that too. If they give you a recommendation on a product, know how to get to the pounds of material. Okay, I do want to say that we're at an extremely exciting time in terms of looking at how to use our nutrients better. And that's good. We've got a lot of people to feed in the world. All the projections say we're going to have, you know, millions and billions more. A lot of them in countries where there's a rising middle class that want better food, more animal products, more meat products, etc. We sure better use our nutrients better, because if you look strategically at the resources that are left for P&K, some people agree that we're using up the higher quality stuff and we're getting down to the stuff that's going to take more processing capital to get to a fertilizer grade. So there's just really exciting stuff going on now to figure out ways to make the nutrient efficiency better. And Josh talked about that yesterday. You want to get more of the nutrients that you apply in the crop. Okay? You want to figure out why the efficiency is what it is, where the loss is happening, and you want to find a way to minimize them. And as I see it, these are the dominant mechanisms, and this is a very gross way of looking at it, that are out there. First of all, one of the things that happens with nitrogen fertilizers is you may add them as an ammonium form, and ammonium may be absorbed onto exchange sites, has that opportunity. But if it's out in the soil solution, it's going to be transformed by the process of nitrification to nitrate. And as nitrate, it's an anion, and it's going to leach. Okay? If you could keep it in the ammonium form longer, you could enhance the possibility that it gets absorbed onto a cation exchange site or taken up by the crop before it reaches too deep below the root zone. So one of the things that were first developed, and this isn't new, those of you that have been around as long as I know that we've had nitrification inhibitors since the 80s, they're improving them now. Nitrification inhibitors are products that can be added to fertilizers or manures, keep the ammonium in the ammonium form to slow down that nitrification process that's biologically driven. The one that's been around the longest is called N-Serve. I don't know who owns the patent anymore because companies keep buying one another out. But N-Serve basically is toxic to the nitrous amonis bacteria. It doesn't kill everything in the soil. It's just toxic to those autotrophic organisms, nitrous amonis. And it's an organic compound, and for a period of time before it is eaten up by the microbes, because it's an organic compound and somebody likes it for food, it actually keeps down the population of nitrous amonis so that that process is slowed down and the ammonium stays in the ammonium form. So there's more work being done with nitrification inhibitors now. I believe there's still a product out there that's called N-Serve, but I think it has been improved since the first stuff that we've been looking at since the 80s. So that's still there. It's often being put in mixtures, and I think it's better than it used to be. There's also the addition of what's called urease inhibitors, and this is really important because remember we're going to be using more and more urea. Okay, in cases where we leave it on the surface, it certainly is subject to volatilization losses. If you could tie up the enzyme that causes that reaction to happen, you could slow down the loss of urea. So there's urease inhibitors, too, that are being added to nitrogen fertilizers that contain urea. Okay? A lot of potential. Okay? They're not, none of these things are worth the money you pay for them in every case. And I urge you to be selective, to keep up with the research, to ask for local efficiency and effectiveness if you're going to pay extra money for these things. Another thing that's come up, and this is really cool, this is to coat fertilizer granules with some kind of a reactive surface that cuts down the fixation. And of course, this is important for phosphorus. You put phosphorus in soils like ours that have a fair content of iron oxides, the phosphorus as it diffuses out can get fixed by reactions on the surfaces of the iron oxides, or if there's soluble iron and aluminum, it can actually form new secondary minerals. So the idea behind coating it with a reactive material is to tie up those things that might react with the phosphorus in this coating so that when the phosphorus moves out, nothing's there to grab it and to change it to a form where it can't be used. Okay? And then last but not least is just covering it with a, I'll call it a semi-permeable membrane that slows down the rate at which the material is released. And this is used with some nitrogen products. Remember, urea is highly soluble. You drop some granules of that on a damp soil and it's going to dissolve and you're not going to see it. Okay? It's there totally. Whereas if it's there in a membrane and water has to diffuse in and then it has to diffuse out, you can slow down the rate at which it's released into the soil and hopefully allow it to stay around longer, that again it gets taken up by your crop. So these are the mechanisms that fertilizer companies are using in their R&D to come up with products now on the market in every single case, and I'm sure there's more work being done, that could get more of what you're paying for actually into your crop. You just have to decide for your use or your client's use, are they going to be helpful? And I want to tell you just about a couple of them that I find particularly interesting and that I'd like you to have a better understanding of. First of all, there's these urease inhibitors. Again, there's going to be a lot of urea that's getting used. The Chinese are making it. They're shipping it all over the world. It's the highest nitrogen content fertilizer of any solid, and it is going to dominate worldwide nitrogen use soon. But there's an enzyme called urease out there, and boy, that booger's all over the place. It's in soil, all kinds of soil organisms make it. It's on residue, and if the urea comes in contact with that enzyme, it breaks down into ammonia and carbon dioxide. Now, this isn't a problem if the urea has been tilled in, but if you've left it on the surface and there's urease there and ammonia and carbon dioxide are released, what happens to your ammonia? Da-da-da, okay? It's gone, okay? So if we could do something to inactivate the urease, tie it up, make it so it doesn't work for a while, and that's the idea behind urease inhibitors. They temporarily block it. They bond with it and block its action, okay? Now, what you want it to do is to block the urease long enough that it rains, because as soon as it rains, it's going to dissolve and move into the soil. This doesn't need to happen for a long time in most years. So studies, and there's been a lot of work done on this, it's not effective all years. Okay, if you have some plots or some replicated strips, and you used a nitrogen fertilizer with urease inhibitor in some strips and without a urease inhibitor here, sometimes you'll find that some years there'll be no difference in yield. Other years there will. A lot of it depends upon, did it rain quickly after you put your nitrogen out? Because if you did, you didn't need the urease inhibitor. On the other hand, if it didn't rain for 10 days, then the urease inhibitor was probably worth what you paid for it. Now, considering you don't know what it's going to do weather-wise most times, you can't plan your application around there, it's probably not a good, it's probably a decent insurance policy if you're surface applying. It has been shown, however, to not be effective in conventional till. If you're going to till in your fertilizer, you don't need to spend money on a urease inhibitor. You put that material under the soil surface, this is going to happen in the soil, it's going to react with water, and it's going to convert back to ammonium and be absorbed. It also tends to not be worth the money where you're banding urea in a limited amount of space. But if you're broadcasting it and you don't get rain, you're broadcasting it on the surface, leaving it on the surface, and you don't get rain, it can be effective. That is, you can get better yield because you got more of the nitrogen in your system. So pastures, for example, okay, it's probably worth, you're not going to till it in, right? You can leave it on the surface. Urea is what's being used. Makes sense there. Here's another one that's pretty cool too. This is Agrium sells this. They call it environmentally smart nitrogen, and it's actually urea coated with a polymer. Okay. Basically, think of this as that semi-permeable membrane. There's some places in there where water can move in. And so water has to move in and then dissolve that nitrogen, and nitrogen has to move out. And a number of studies have compared this with applying all your nitrogen pre-plant as urea, as corn, applying all your nitrogen pre-plant as ESN, or side dressing. And what they found in some work that Greg Binford did in Delaware was that using ESN for your full nitrogen recommendation pre-plant gives you a better yield than using just urea, but it's still better to split apply your nitrogen and side dress. So it's kind of intermediate between the two. So there are certainly cases where this might be a product that you'd want to use. And this is an example of taking a soluble material, putting a semi-permeable membrane around it to slow down the rate at which a soluble product actually moves out and is released into the soil. Okay. Okay, so now we're going to talk about liming materials. Okay. Remember, we talked about why liming is important yesterday, but now we're going to talk a little bit about their composition and talk about the advantages and disadvantages of using specific things. The two products used most in agronomic crop production are calcitic limestone, sometimes just called limestone. It's primarily calcium carbonate, or dolomitic limestone, which is a calcium magnesium carbonate. And the most common way of expressing lime strength or effectiveness is calcium carbonate equivalent. Our state still hangs on to the calcium oxide expression, but most states have changed from that. Again, it's all based on molecular weights. You remember that calcium carbonate has a molecular weight of 100 grams per mole. So all the conversions back and forth are just based on molecular weights. Okay? You can see, though, if limestone has a calcium carbonate equivalent of 100, dolomitic limestone is a little bit stronger, almost 10% stronger, in terms of liming effectiveness per ton. Okay? Now there's two other products here, burnt lime, which is calcium oxide, and slake lime, which is calcium hydroxide. They also are liming materials, and there are cases where you might want to use them. They are quite concentrated, number one. They're much higher than 100. I mean, not just a little 9% dolomite. They're 80% and 35%. But they have their use, but they have their downside. Okay. So first of all, if you'd ever decide, and you might for a horticultural crop, if you were growing a calcium-sensitive crop like tomatoes on some new ground that didn't have the appropriate pH when you started, you might want to actually invest in these higher reactivity limes so that you didn't have a crop loss due to blossom end rot. But short of that, you probably wouldn't want to. A ton of limestone has the same liming effectiveness as 9/10 of a ton of dolomitic limestone, 55/100 of a ton of burnt lime, or 75/100 of a ton of slake lime. So if you're going to use these other materials, you need to add them at the appropriate rate. Now, a ton of calcium oxide is way more liming effectiveness than a ton of calcium carbonate. So again, you can use the ratio of molecular weights to adjust your rate if you're going to use one of the more highly concentrated products. Another thing to be aware of is that these two products are also caustic. That is, if you get it on an open cut, they will burn your skin, and calcium oxide is particularly caustic. So I looked up solubilities of things, and this is how many grams of that stuff that would actually dissolve in a liter of water. And you can see that limestone's not particularly soluble, okay? And dolomitic limestone is actually 6 times less soluble than the calcitic lime is. You would use it, however, if you needed both calcium and magnesium. If you needed to lime your soil and your magnesium FIV was only 45 or 50, then you need to invest in the dolomitic limestone, even though it's going to react a little bit slower, because you need both both the liming effect and the magnesium. Okay? Calcium oxide, I can't even find a solubility expressed this way, which implies that huge amounts of it would dissolve in water. I'm sure there's some point where it doesn't, but I haven't been able to find where that is. Calcium hydroxide, much more soluble, 1.9 grams per liter. It's 100 times more soluble than that. So again, if you need a fast-acting material for some specialized application, you can invest in these other products. Now, they're expensive. Don't misunderstand yourself. They're expensive. Okay? Calcium oxide is also exothermic, and it's used actually in one of the PFRP products that Allison mentioned, biosolids, to basically pasteurize it, to increase the biosolids to the point where it meets the temperature requirements for pasteurization. Another important aspect of your liming material, beyond your calcium carbonate equivalent, is how big are your particles. And typically what you're given on a lime label is the percentage of particles passing through various size sieves. Now, what sieves are in your regulations varies from state to state. In Maryland, you guys in New Jersey, you'll have to go back and check. In Maryland, it's what percentage passes the 20 mesh sieve, what percent passes the 60 mesh sieve, and what percent passes the 100 mesh sieve. And if you ever were in a soils lab where they were separating out sands, you know that you can buy these nested sieves with certain sizes. Well, what you do, if you send a lime sample to a lab and you want to know the particle size analysis, they weigh out a certain amount, put it in the top, and put this whole family of sieves on a shaker and shake it for an hour. And then they see how much is caught on each sieve. Now, a 20 mesh sieve has 20 wires per inch, which is already pretty small. 60 mesh sieve has 60 little wires per inch going both directions. And 100 has 100 wires per inch going. So the stuff that passes 100 mesh sieve is pretty fine. Okay. Now again, some states vary in terms of what mesh they look. Some states just require that you tell the farmer what the percent passing each mesh is and let them figure out what they're going to do. It really depends. It really varies a lot. The lime regulations vary quite a bit from state to state. Okay. Here's a study from Result. This comes from the liming monograph that the American Society of Agronomy put out. And this is showing you the reactivity of various separated out particle sizes of lime in terms of how long it took for things to change or not change, and also the pH. So we started at a soil that looks like it had a pH of about 5.1, and when you didn't add any lime, the pH continued to go down over the period of 3 years that they monitored this particular experiment. If the material was 20 to 30 mesh, there was a slight, and the same rate of lime was used in all cases here, of course. Slight increase, pretty slow, maxed out about 1.5 years, and then dipped off. Okay, 40 to 60 mesh, this is even finer. You got a much more rapid change. Look here, by a couple months, you're already, certainly by 4 or 5 months, within that growing season, you're getting an impact. It maxed out much higher, maxed out at about 6.5 before it too leveled off. And the stuff that actually passed through the 100 mesh reacted extremely rapidly, peaked quickly, and then had a long decline. So liming materials typically are, you know, they're not all 100. I'm not saying you want all greater than 100. First of all, it's going to be expensive. You can see where you sort of want a mixture, right? You want the rapid reaction from some of your lime product, and yet you want the sustained reaction that some of the coarser particles can get. In fact, your liming materials are going to be a mixture of particle sizes. Okay. Want to talk just for a moment about soil amendments and conditioners. There's a fair amount of controversy about their use right now on cropland. These two are regulated by Maryland state regulations. Those of you that are from other states need to find out what's going on in your state. But an amendment or a conditioner is a material about which no nutrient claim is made. But it's believed to enhance plant growth somehow, or improve the physical or chemical conditions of a soil. Okay? Now, if a conditioner or amendment contains nutrients, You have to integrate that material's use into your nutrient management plan and account for the nutrients that you're going to get from it. Now, not all amendments or conditioners have significant nutrient content. Many do. Examples of some of the ones that are applied in Maryland that do definitely have nutrient content are chicken processing waste, whey from cottage cheese production, vegetable processing waste. They have nutrient compositions, concentrations similar to manures. And you can't just say, well, I'm not using it for its nutrient content. It's a conditioner. Okay? That's not going to cut it. You know, if it has nutrient content, you need to integrate it into your nutrient management plan just like you'd integrate a manure or another kind of organic waste into your nutrient management plan. Okay? So we've breezed through fertilizer and liming materials. Are there any questions? Can you ask a question into here? Thank you. It's on.
Yeah, okay. On your last point about conditioners versus fertilizers, isn't there some requirement that MDA has that if it has a fertilizer value that it be registered as such versus a conditioner, or no?
I don't think so.
No? Well, I'm sure you'd know.
I think the
okay.
user declares what it is, don't they? Here.
The State Chemist's Office of MDA requires that any material that's going to be land applied that has a claim of doing something to the soil, changing its physical characteristic, chemical characteristic, or makes a claim of improving plant growth by any means, be registered with them. Now, most recently, Nutrient Management Program has been working with the State Chemist's Office to clarify this kind of confusion about whether it has, quote, nutrient value or not. And so with a survey of the materials that they have been registering over the past year or so, we have found that there's a lot of things that they register that do have significant or appreciable nutrient content of some sort. And we're trying to formalize the requirements of having everything analyzed with a few exceptions for materials that will be land applied. So no longer will it be just, as Trish said, oh, we're not making any claims that this is going to do anything, but, you know, Mr. Farmer, this is great, so we'll put it on your field. Mr. Farmer needs to have a nutrient management plan that includes that material. He has to have an analysis of that material before it's applied, and then apply it at an appropriate rate depending upon his soil tests, his crop, yield goals, and everything else he needs in his nutrient management plan.
Often you'll hear it described as wet lime or dry lime. What's the difference?
Well, wet lime obviously has a higher moisture content. Some limes are very dry. Some people want the wetter lime because you don't get as much loss due to blowing of fine particles away. You do need to recognize that the lime requirement given in your nutrient management plan assumes pure, fine, dry lime. So if you buy a limestone and it has significant amounts of water in it, you're going to want to adjust your rate so you actually get the lime benefit you want and can't overlook the water. So I believe they still need to label it the same way in terms of what sieve size it passes, but you may need to make an adjustment if it's more than a modest amount of water. I've seen some limes that were only 75% solids. Well, that's enough. You need to make an adjustment and change your rate a little bit because 25% of that's water, and your lime recommendation assumes pure, dry, fine lime. Any other questions? Yeah.
Is there any liquid lime in Maryland?
I can't answer that. Does anybody else know? Do you know of any liquid lime in Maryland? That was pretty fine, and it's usually suspended, right? It was pretty expensive to use years ago when I knew about it. Okay, so maybe that's why there isn't much. Yeah. Okay. I don't know of any liquid lime in Maryland. Any other questions?